Welcome. Today's notes worksheet is entitled Quadratic Functions Day 3. And the Day 3 lesson really just represents a review of some of the algebra and then some culminating applications that we're going to do together. So let's just see what's on your sheet here and then highlight one or two things and then get ready to roll. So we've looked at two forms of a quadratic function to this point and all the algebra that goes behind it. Standard form, there we go. And remember to find the vertex, which is really the primary characteristic with these applications, opposite of b over 2a, and then plug it back in to get that max or min, depending on if it's opening up or down. In completed square form, and that was on the previous notes worksheet, this is what it looked like. We did some of the algebra with the conversions and then also working with that. The nice thing about that one is the vertex is embedded in the function, so the vertex is h and k. And it looks like I put a little asterisk by it and an exclamation point behind it. What do you say we box this up? If we have the vertex, if we are modeling a parabola and the vertex is given, we're going to use that form, no doubt about it. So as I mentioned, most of the applications do revolve around the concept of vertex. I'm hoping at this stage, just algebraically, you're comfortable with those pieces. Also, sometimes you need to solve an equation that is quadratic in nature, so as long as it is set to 0, something like this, we know different methods to go ahead and do that. If the numbers are really bad, we'll just use the program on the calculator, but really it's factoring, it's undoing the square. Again, just rehashing this time and time again. Some good stuff with this, of course. A lot of completing the square. And last, of course, would be the quadratic formula. All right. So again, that's just a very quick summary of what we've done over the last couple days. Some great algebra that has been really behind these two forms. So let's just do 3 examples. That's all I have. So this is a great maximizing area problem, just a variation on the one we saw in the previous notes worksheet. And at this stage, we're going to try to do most of this just non-graphing calculator oriented. We'll use the calculator to help us do some of the actual calculations, but we're not going to graph it. So at this stage, and the hope is after this problem, I should be able to give you really any type of maximization of area problem, optimizing area, and you'd be able to kind of solve it. So let's try it. Example 1. A dog owner has 150 feet of fencing to make 3 side-by-side rectangular kennels. Draw a diagram and label the length x and the width y. Sounds wonderful to me. So let's just go ahead and 3 side-by-side kennels. It doesn't matter if they are equally spaced for right now. Do it however you'd like. But there are 3 side-by-sides, and we've got 150 feet of fencing to make up that. And it's just x and y. However you want to do that's fine by me. Okay, good. All right, now it says write a function for the enclosed space in terms of the length x. So we all know, of course, the area of the whole thing, which we will try to optimize in just a moment or two. The area is x times y. So let's kind of get this going here. I'm going to try to find as much space as possible on my board. I think I'm going to need it. So hopefully I left you enough on this notes worksheet. As we've said before, what we want to do is construct a function for the area in terms of a single variable. So right now, we have an extra variable there that we're going to have to remove. Substitute for, I guess. Now, let's go for it. We need that second equation in order to allow us to replace that y. And as we have seen before, and again here, it's all based on the amount of fencing used. So I guess I would ask you this question is, what is that 150 feet of fencing made up of in terms of x and y? So if you look, I've got my 3 side-by-sides. I've got a bunch of lengths and a bunch of widths. So let's say I've got 1, 2, 3, 4 lengths, 4 x's. So it looks like the 150 feet is made up of 4 x's, and it's made up of 2 y's, top and bottom there, just according to my diagram. All right, so we have a fixed perimeter, so to speak, or a fixed amount of fencing, and what we want to do is optimize the area. And this comes up with a variety of problems at this level. 1 quantity fixed, 1 quantity optimized, either maximizing or minimized. And this is a good one. I like kind of working with this piece. So everyone, let's solve for y. Remember, replace y, then you need to solve for y over here. So I'm going to bring that 4x on over. And I have that. Then I'm going to divide by 2. Just make sure you divide everything by 2. And it looks like I have 75 minus the 2x, and that's equal to y. All right. I circle, I draw the arrow, makes me happy. That's going right in there. And so now we can start to see that that area is equal to x, not times y, but x times the 75 minus 2x. Hope everyone is clear on that particular piece. Now what we're going to do, of course, is distribute that in. And when I distribute that in, I have area in terms of this. I'm getting a 75x minus the 2x squared, just kind of thinking out loud with that. Let's see if we can do a little better. So we have now area in terms of x. And just to make it in that nice standard form there, that's looking great. All right, so any variation on a fixed perimeter, maximizing the area. In this case, we're able to come up with a nice quadratic to allow us to pull that off. And again, mathematically, there are theoretically an infinite number of x's that would produce an infinite number of areas. There is one value of x that will optimize, or in this case, maximize the area. And that's C and D. I've had you do this before on a previous notes worksheet. I'll have you do it again. Anytime you're working with a quadratic, you see the a value is negative, and it's asking to maximize that quantity. We know we're going vertex on this. So this naturally led to the standard form of a quadratic equation. It wasn't a situation where h and k came into play. We would actually now have to find that vertex, and we're going to do that using the standard form right here. So again, I would not graph this on the calculator. What I would do is just a calculation. I think it's better. I think it's quicker. So let's give it a try. So first and foremost, find the value of x that will maximize the area. So the input to produce the maximum is the opposite of b over 2a. So negative 75 over 2 times negative 2. There we go. Now if you have a calculator handy, take negative 75 and divide by the negative 4. I'm getting 1875 just looking at that. And I think this was in feet. So I'm going to go ahead and put that right there. And, you know, I'm just always thinking about what things represent. Helps me kind of seeing it with my picture. So that is 18.75 feet right there. Absolutely great. And again, the math was relatively simple. No use stressing over a window to see a graph. I think this works out better in my opinion. Well, now remember, we want to maximize the area from there. This is not going to give me the other dimension. This is going to give me the dependent variable, which is the area. So I want the area when x is 18.75 feet. And so now if you remember how vertices work, we take the x value, of course, and we put it back into the function, and we get the output. So negative 2 times 18.75, square it, 75 times 18.75. Okay, I'm going to step back for just a sec, make sure that is legitimate, and I'll put a little equals right here. And again, we'll use our calculator, but just obviously to get that calculation squared away. So let me go ahead and bring that on up, and all right, let's see. I've got negative 2 times 18.75 squaring it, and then plus, what did we say, 75 times 18.75. That went in, that comes out. That is our maximum area. Beautiful. Okay, so 703,125 square feet. Again, that's not y, that is a. So I'm going to kind of put this in here, 125 square feet. That's the best we can do in terms of the space enclosed for these 3 kennels. Okay, good. So many different ways to then do part E. It does say what is the width. So obviously, guys, we have the length, we have the area. Is there a way to calculate the width? Yeah, and again, I could think of a couple ways to pull this off. I think most students like just taking a look at this. As long as you know that this is the area, just take that and divide by 18.75. That should give you the width. Another way, I'm just kind of staring at my board here. There's so many different mathematical relationships. In this case, if I have the x, can I come up with the y? Well, yeah, sure. 75 minus 2 times 18.75. Well, regardless, I believe if you do one of those two things, I think you get a width of 37.5. I seem to recall that piece. So what is the width? I'm just going to do it up here that the y was 75 minus 2 times that. I'm just going to do that, but obviously, however you do it, it makes no difference. As long as you get that 37.5. And I guess this was just the last culminating piece here, not that it's a big deal. But it says, what are the dimensions of each kennel if they are the same? Again, that was never initiated in the problem, and it actually didn't affect the problem at all. But if they're the identical 3 kennels side by side there, I don't know, it looks like we have the same length. Everyone okay with the fact that the width would just be a third of that? Just here's 1, here's 2, here's 3. So if we want to just take that and divide by 3, actually it looks like it's going to work out pretty well. So it says, what are the dimensions of each kennel if they are the same? I'm getting that 18.75 feet. And that would be by, what's that, 12.5 feet? Just what I'm seeing when you take that and divide by 3. So 12.5 feet. Cool. Yeah, really good, fascinating problem. So really, again, any variation on this should be able to pull off, draw the picture. And if you can come up with this equation, I really think you're on your way. And then it's vertex, guys, vertex. Notice I did not graph it and came up with it really quite easily. Okay, good. Fixed quantity and then optimizing a second quantity. Good. All right, let's go get example 2. So good one right here. I'm going to have to draw this one. I remember interpreting the information as not so straightforward, but regardless, I think we could pull it off. So the Golden Gate Bridge, which spans the San Francisco Bay, has towers that are 746 feet tall, 4,200 feet apart. The roadway is 220 feet above the water. The bridge is suspended from 2 huge cables that are parabolic in shape and touch the road surface at the center of the bridge. Write a model for the cables there. Alrighty, so let's see what's going on. First order of business, everyone, is let's get the roadway sort of squared away here. Left a lot of room to kind of pull this off. And then it looks like I've got one tower here, something like this. Again, I'm trying to remember the schematics behind this. Something like that. And then here are the parabolic cables that come on down in between the 2 towers and touches the road surface right in between. So something like that would do. And here's what I recall with this. First and foremost, they are 4,200 feet apart. So let's go ahead and get that taken care of. 4,200 feet. That looks good right here. And then I'm also looking, the towers are 746 feet tall, and the roadway is 220 feet above the water. So I think that does have a bearing here, everyone. So this kind of goes down to the water area, and just for lack of a better description on this, kind of like this, sort of coming down like that. So this is still an extension of the tower. I guess I should kind of do that piece down to the level of the water, wherever that may be. And let's see, so 220 feet above the water. So this is 220 from here to here. Again, just kind of following the lead from the information. The towers are the 746 all the way through. So that's what I remember on this one. So that's the 746. And again, I know it's difficult to kind of interpret the problem here. I seem to recall this one and the information I got online, and I think that should fit. So we need to model this. And we're going to model it algebraically. And remember, you're basically going to superimpose a coordinate plane directly on top of your little diagram sitting on your paper there. You can do this any way you'd like. I just happen to believe you probably want to make it as easy as possible for yourself. For a parabola opening up, unlike opening down, by the way. But for a parabola opening up, I think it's the easiest thing to do is to put that vertex right smack in the middle there on the origin. So as I put my coordinate plane in place, I think just having the origin be the vertex works out pretty well. And again, if you want to come up with something different, I won't stand in your way. But I like that 0, 0. It is the vertex. And remember, if we have the vertex, which we do, conveniently enough, there's h and k. Now, I know this isn't easy, just the way I kind of drew with all the numbers here, but I would argue you could probably come up with an ordered pair for that point and that point. We only need one, but I'll bet you can come up with both if I made you. Let's do the one on the right. Might as well. So what is that ordered pair right there? Take a sec and think about that piece. What would be the x and what would be the y? So look at your diagram for a moment and see if it clicks. All right. Well, I'm getting an x of 2100. Right? 4200 all the way across. We went dead smack in the middle there, 2100 to the right. Also, the y value just represents above the roadway the way I did this. So above the roadway there, it's not 746. It looks like it's going to be, I'm seeing 526, this minus this. So I'm seeing that as 526 feet, and that should have been given in the problem. It's kind of silly that it wasn't. But this was the information that I got all the way through. So there is your x, and there is your y. And let's utilize that. I think that's great. Notice it looks like this one is completed square form. So I'm going to go ahead and get rolling on this. Don't forget the squared. And we have everything but a. I know a is going to be positive, and I hope you do too. We have a parabola opening up. I know a is going to be tiny. It's going to be a really small number, very close to 0, because it's such a wide parabola. So let's say I've got 2100, and then minus, what was that, h? Oh yeah, just 0. And then plus 0. Okay, good. So, I'm just going to play it out as consistently as I can here. 2100 squared. I don't have that off the top of my head, so let's get a value on that. And so here we go, 2100, and let's square that piece. So 441 and 2, 4, 6 zeros on that. Okay, so there we go. And again, officially there's a plus 0 there. You, of course, would bring this on over, and then you would divide by that piece right here. Long story short, it's just going to be 526 divided by that number right there. And we're going to go ahead and get our decimal on this, and let's see what we end up getting. Come on. So how about this? I do 526 divided by that answer. And, ooh, interesting. All right, so I've got, oh, I actually just caught myself there. It looks like I accidentally typed in an extra 0 on my calculator there. I don't know if you guys caught that. But let me remedy this a little bit. So I think that's going to cut off a couple of those. Sorry about that. So how about 1, 2, 3? I was wondering, it did look a little too small for my taste, but I'm thinking it's something like that. So let me go back and do it one more time. Here's where I did it. Accidentally tapped an extra 0. Should have been 2100. I typed in 21,000. Okay, so let me see. Now I can fix that. Not a problem. 526 divided by 441. And shouldn't change things up dramatically there. Yeah, I like this a little better. This e-4 here just means times 10 to the -4th, which means you would move that decimal 4 units to the left. And when I do that, and this one, again, extremely small, 1, 2, 3, and then 11927. There we go. Not bad. Okay, so I have an a value that matches this parabola perfectly. So now we're ready to model the infinite number of points on the parabolic cable. Y in terms of x. So the way I see it is it's 0.00011,927, And then it would be x minus 0 squared, which by the way is just x squared, and then plus 0. I think that's it. Oh, that's going to be nice and easy to work with, huh? So it's just a benefit of having the vertex at 0, 0, because x minus 0 squared and then plus 0 really just simplifies things out. Okay, letter B then. Find the height of the cable at a distance of 1,000 feet from the center. All right, so in this case, I'm going to underline this piece. Always want to be careful about how it's phrased. 1,000 feet from the center, so let's start here. If it said 1,000 feet from the tower, that would be different. We would be coming in from the tower 1,000. In this case, though, we start at the center and go either left or right 1,000 feet. I'll just go to the right there. It's easy, and that's what I'm thinking. So something like that, 1,000 feet from the center. Okay, which means because I came off of an x value of 0, 1,000 feet from 0 is just going to be 1,000. So I'm seeing this as just really f of 1,000. So got 3 decimals there, 11927 times the 1,000 squared. Pretty nice. And I think I can hack this. A couple zeros, moving that over. It just has to be about 119, what I'm seeing there. And this is in feet, right? Yes, feet. There we go. So I'm seeing that piece right there. And you know, just kind of looking at that. This height is 526. I go 1,000 over. Yeah, I'm still pretty far down my parabolic cable. So about 119 looks really, really adequate in this case. Okay, last one right here. Determine the distance from the center of the bridge when the height is 300 feet above the roadway. So now, everyone, it looks like I'm going to give you a height of 300, maybe somewhere in here, give or take. Notice it's going to sort of happen in 2 spots, one to the left of our vertex and one to the right of our vertex. Let's see if we can get both of those. I'm hoping you agree. You know, when I talk about the height being 300, I am talking about the y value being 300. And this one shouldn't be too bad either. We have such an easy equation to work with. So I'm hoping you would agree to solve for the variable. You're going to have to divide by this monstrosity of an a value right here. And then what do you think? We just undo the square root it? If it's okay with you, I think I'll try to do those 2 steps in one shot. And let's see what we end up getting there. So 300 is our y value. I'm going to divide that by 0.000. Let's make sure I don't tap too many zeros this time. 11927, I think that was our a value. And I get that right there. And then what do you say we square root this thing right here? Get that. Ooh, looks pretty good. And so I'm getting an x value. Don't forget, when I undo the square, I do officially take the plus or minus. So 1585, I saw about 97, I could be wrong on that, but about 1586, give or take, feet, again, from here and from here. So 1 to the right, making it positive. I guess that would be in this vicinity, and then 1 right here to the left because of the symmetry in that vicinity. So distance from the center, you know, really it's just the left and right. There's your distance. Wow, wonderful. So we've done one in standard form. We've done one in completed square form. Looks great, really does. Let's do one more calculator problem. So here we go, example 3. Let x be the speed of the car in miles per hour. First, find a quadratic regression for the braking distance for this car. Interesting. And then an insurance investigator finds skid marks 165 feet long at the scene of an accident involving this car. Determine how fast the car was traveling when it made these skid marks. Wow, fascinating. Well, let's do a couple things first here. Just didn't give you a ton of info to work on. But it looks like the length of the skid marks is dependent on the speed. So I've got x for the speed and y, the length of those marks right there. And that's good. So what we're going to do is come up with a relationship between the two, and I believe this will be quadratic in nature. It's a good one for us to do again, just as a refresher from the first day's notes worksheet. Remember, guys, it's a 3-step process. Enter the data, view the data, model the data. So a couple things first. If you have anything in the y equals, please clear it out. If you have stat plot, I'm going to turn mine on. I don't think it's mandatory, but mine's on right there, and I'm going to keep it on for right now. And then let's go stat and hit edit for me. I have data in there already from previous lessons, so remember how it works. Go up to the L1, hit clear, enter. Then go up to the L2 and hit clear and then enter. All of that is out. I will try to type as fast as I can. You guys do the same, of course. Okay, I'm rolling nicely here. Again, I've been tapping a little too much at this board, so I don't want to do anything extra. Okay, good. Got those. So at 20 miles an hour, the length of that mark for this car is 29 feet. Again, as you go faster, the length of the skid mark, the braking distance, so to speak, is getting larger and larger. So let's see. Okay, got them in. Now, zoom, hit number 9. So enter, view, and model. And you can see this doesn't have that linear feel to it, in my opinion. It looks like it's more of sort of a wide parabola right here. Again, we would make that interpretation. According to this, I do want a quadratic regression for it. That apparently is the relationship between the two. So let's go ahead and get that quadratic kind of fit in those marks right there. Looks like obviously a parabola opening up, so you know the a value is going to be positive. I'm going to hit stat, everybody, move it over to calc, quadratic regression. I like pasting it into the y equals. It is totally not necessary, but I hit the vars button, move it over, function, y1. I do that myself just to make sure it's all legitimate. And that looks pretty good right there. I'm seeing an A, a B, and a C. That'll match this data set. Let's put that in place. So if you guys are ready, the quadratic regression would be this. I go about 3 decimal places out on these. If you want to go further, that's great. Obviously, the further we go, the more accurate it's going to be. Oops. So there we go, 8, 5, and 7. All right, that's good. And just before we get into the last piece of the day, let's see, I want to go hit graph again. And there it is. There's, a nice looking parabola. Looks like it's fitting that data quite well, to be honest. And now what we want to do is, let's use the regression. I'm going to try to do this algebraically here, although I think we'll use the calculator for quite a bit of help. But let's read the rest of the problem. An insurance investigator finds skid marks of 165 feet long at the scene of an accident. Determine how fast the car was traveling when it made these marks. All right, I'm hoping you agree. The 165 is a y, not an x, which is huge here. Okay. Now, how do we deal with something like this? Well, I do want to solve for x. In this case, though, it's a quadratic. This is not quite in our default form right here. I think I do want to go ahead and subtract the 165. So it's not as easy as if I was given an x solving the y. In this case, given the y, solving the x requires quite a bit more work. So now does it look better by bringing that 165 over? So I'll have a 490x right here. And then actually, I have this on my paper. When you do the 15 minus this, you get 149, 143. Okay, great. Now it looks pretty good. Think about this, because again, we did it on the front side. I've given you a y. Now we want to solve for x, and now it's in the form that we're comfortable with. I would factor, I would undo the square, I would complete the square, I would do quadratic formula, and without question, it looks like quadratic formula is the way to go, especially as the calculator is going to just quickly spit out those answers for us. So let's do that. I'm thinking quadratic formula program. You could do it graphically. I think it's almost easier just to quickly do it like this, though. So quadratic formula, let's do that program, guys. Get comfortable with that piece. A, 0.056. B, what's that, negative 0.49. And C, there we go. C is, there it is, 149, negative 149.143. Okay, let's see what it gives us. So it gives us two answers, of course, because every quadratic does have two answers. I think we're talking about x, and that's the speed. That one doesn't make any sense whatsoever. So I'm thinking that's the one right up there. It looks like x is equal to, I get 56.167, give or take, miles per hour. Pretty neat. Very cool. Looks like I missed a decimal there. Let me put that in. That's great. Now it's perfect. Cool. Well, again, guys, just quadratic regressions. Should be comfortable with that. And I love this piece now down here. It's kind of the culminating piece. Not a vertex. We're not maximizing or minimizing anything. We're actually solving the quadratic equation. So make sure it's set to 0, and then use your program. That's fine for these numbers. All right, good. Good culminating notes worksheet here. Let me know if you have some questions as you try some of the applications on your own. Thank you so much for listening.